begin, what are herbicides and where do they come from? According to the EPA, an herbicide is a class of pesticide that is used to control undesirable vegetation. They are most commonly used in crop farming, forest management, and suburban areas. The first herbicide was produced in France in 1896 to control broadleaf plants in farming. However, it was World War II that spurred the development of new, highly toxic organic herbicides. These chemicals were researched due to their high military potential to remove heavy vegetative growth in war zones. The first modern herbicide to be created was 2,4-dichlorophenoxyacetic acid. However, since it was created during wartime, the original publisher is contested and unknown. Herbicides were not used in World War II, but were used later. For example, Agent Orange was used during the Vietnam War. Herbicidal warfare is now banned and considered illegal because of its horrific, long-lasting impacts on the human body. From its beginnings in war, weed science has changed significantly since the 1970s. Most importantly, new herbicides have been created, resistant crops have been produced, and herbicide laws have been modified. Today, the most commonly used herbicide is glyphosate. This is because of the rise in genetically engineered herbicide-tolerant crops. Herbicide-tolerant crops now account for 56% of global glyphosate use and continue to be used extensively in the United States. Since 1974 in the U.S., over 1.6 billion kilograms of glyphosate active ingredients have been applied. This accounts for 19% of estimated global use. The widespread use of herbicide has caused significant weed resistance and is an important problem to tackle. Additionally, while the toxicity of glyphosate is still debated, it is still used today, unlike some of the extremely dangerous and toxic herbicides that were used in war.
Okay, so now that you know a little bit about herbicides, we're going to talk about how they are produced. And specifically, we're going to talk about 2,4-D because it's one of the most commonly used herbicides and it's produced in very large quantities, so its synthetic pathways are widely studied and known. And there are two main ways to produce 2,4-D. The first is the condensation route, in which you take two larger molecules and put them together to get 2,4-D. The second most common is the chlorination route, in which you start with a molecule that closely resembles 2,4-D and you chlorinate it to get your product. Today we're just going to talk about the condensation route. So this overall reaction, here's what it looks like. You start with an alcohol, 2,4-dichlorophenyl, and a carboxylic acid, chloroacetic acid, and you perform a substitution reaction at the primary carbon on the acid to get your product 2,4-D. This reaction is performed under basic conditions, and the reason we do this is to increase the strength of the nucleophile. So if we consider our alcohol, 2,4-dichlorophenyl, when we add sodium hydroxide, what we do is we deprotonate the OH group and give us the salt form of the alcohol. And the reason we do this, the alcohol in its protonated form is a much weaker nucleophile than when it's deprotonated, in which we have a stronger nucleophile that can better undergo the substitution reaction needed to perform to get the product. So this reaction is what's known as a Williamson ether synthesis. So we have our deprotonated alcohol, our strong nucleophile, and in the acid we have this chlorine, which is electronegative and creates a cationic center at this primary carbon. The alcohol performs a nucleophilic attack. The chlorine leaves, and we get the salt form of our product. We can then add HCl in order to convert the product back into its acid form, and then it can be extracted into an organic layer. So once it's converted back into its acid form, 2,4-D is actually rarely used that way. Instead, what we'll do is convert it into an amine salt or an ester. And one of the most commonly used amine salts is 2,4-D dimethylamine. So if we take 2,4-D in its acid form and we add dimethylamine, which is a base, we'll end up deprotonating the acid and getting the salt form 2,4-D dimethylamine. And the reason it deprotonates is because the pKa of 2,4-D in its acid form is much lower than the protonated dimethylamine, and so we end up with an equilibrium constant that strongly favors our products. It can also be utilized in an ester form, and these are produced through what's known as the Fischer esterification, and this is an acid catalyzed reaction. So what happens is the acid protonates on the carbonyl. We create a cationic center at the carbon, and an alcohol with whatever group we want to substitute will attack. After a proton hop, water is formed, which is a great leaving group. And after the proton leaves, we regenerate the catalyst and get the ester form of our product. And we have to make sure that we perform this with excess alcohol because the acid and the ester derivative are on the same order of reactivity, so we perform it in excess alcohol to utilize Le Chatelier. And so this is a little bit about how modern day herbicides and specifically 2,4-D are synthesized.
All right, so how do herbicides actually work? How do they actually kill the plant? This process is called its mode of action, and it can come in either the physical or biochemical form. And an example of a biochemical herbicide would be an herbicide which inhibits the photosynthesis process within multiple cells within the plant, and eventually leading to its death due to lack of energy. And another example would be, of a physical one, would be breaking down the cell wall structures within the plant cells, causing the plant to deteriorate and die out in time. So we're going to key in on one specific mode of action for this presentation called the auxin mimic. One of the more common mode of actions in herbicides, this herbicide class kills the plant through the imitation of auxins within the plant. Auxins are growth hormones common in plants, which act as regulators for many growth and behavioral processes within the plant. And typically these auxins are found in trace amounts in the plant, as too much of them can be dangerous towards the plant and cause death. The auxin mimics take advantage of this, sharing many key chemical features to the indole-3-acetic acid, IAA, which is the common auxin in plants. They cause a sort of auxin overdose when they're applied and absorbed into the plant, and they lead to rapid and uncontrolled growth in the plant cells, which obviously will effectively kill the plant. So, what are these key chemical features that the auxin mimics share with IAA? The main chemical features you need in your auxin mimic are a strong carboxyl group after the dissociation of the proton, and an overall positive charge on a planar ring attached to this negative carboxyl group. The first one we're going to look at is clopyralid, which has, as you can see, the carboxylic acid, which would dissociate, leading to the strong negative charge on the oxygen. And it also has the positive charge on its planar ring due to the two strong electron withdrawing groups in chlorine. Similarly, p-chlorine has 3 of these chlorines and an amine group as their electron withdrawing groups, and this same carboxylic acid group, which would lead to the negative carboxyl in the positive planar ring. And finally, the most common form of weed killer herbicide is 2,4-D, with 2 chlorine groups attached. It has those electron withdrawing groups creating the positive charge, and the carboxylic acid on the end would obviously lead to a strong carboxyl negative charge.
Herbicides are clearly very important for killing weeds and enhancing plant and crop growth. However, herbicides can potentially pose both environmental and health risks. One great example of this is Agent Orange. Agent Orange was an herbicide used by the United States during the Vietnam War to defoliate the Vietnamese forest. As you can see, nearly all plant life was destroyed. It is composed of a 1-to-1 ratio of 2,4-dichlorophenoliacetic acid and 2,4,5-trichlorophenoxyacetic acid. As you can tell, the structures of the two are very similar, with the number of chlorine substituents on the benzene ring being the only difference. Aside from the immense environmental impacts Agent Orange had during the war, it was later realized that many soldiers suffered health complications from being exposed to Agent Orange. As Wesley previously discussed, 2,4-D is still commonly used today, and 2,4,5-T is chemically very similar to 2,4-B, so neither of these were really believed to be health hazardous. However, it was discovered that in the synthesis of 2,4,5-T, at high temperatures, it can undergo an undesired side reaction to form 2,3,7,8 tetrachlorodibenzoparadioxin, which is a known carcinogen. Normally, 2,4,5-T undergoes a substitution reaction. It's very similar to what Wesley discussed for 2,4-D. So it forms this salt intermediate, and under acid catalyst conditions, the hydrogen will protonate the oxygen, and then since chlorine is a moderate nucleophile, it can undergo a substitution reaction at the primary carbon to produce 2,4,5-T. However, at high temperatures, two of these salt intermediates will simply bond to each other. Then through the loss of sodium chloride, it forms this dioxin structure with two benzene rings connected in the center by a heterocyclic ring containing oxygen. Dioxin is a known carcinogen, so it is clearly bad for human health. Since it is perfectly symmetric, it is nonpolar. And fatty acids with their long hydrocarbon chains are also nonpolar. And since we learned that like dissolves like, dioxin is easily able to dissolve into fatty acids. And then since it has two benzene rings as well as a heterocyclic ring in between, it has a very strong structure that is difficult to break down. As a result, this dioxin structure that is a known carcinogen is easily able to dissolve into the fats of humans and stay there for long periods of times. So that wraps up our presentation on herbicides and the synthesis of them, how they function in plants, as well as the environmental and health risks that they possess.